This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Right, you say that the gain margin is about 10 dB, right?
Okay, so well, I'll explain this again at the beginning of the section.
Yeah, and the C part, the recording is not captured.
Oh.
Yeah, the total C part. And I think that it should not be the 10, because it should be, because we find that the 30 degrees phase margin at a point here, right? And then we got a value here, right? And then we can make it times a K and then equal to 10 dB, 0 dB,
Yes.
right? And then the K is roughly equal to negative 20 dB, because like here, right?
Yeah, if you draw it there, it is.
And I think that the gain margin here, if you say that it's 10 dB, it should be 10 minus 20, it should be negative
Yeah, well,
10.
so it really depends on like where you estimate that line, right? So if
I
you
think it
draw
should be negative something, right? Because the K here,
No, because your K is below 0. It's negative, right?
yes, it's negative K.
So it's below 0.
Yes.
So, which means,
Uh-huh.
like, where is it? This line, right? So these two almost cancel each other, right?
Yes.
But leaving a little bit positive part, right?
Yes.
And then you,
Five
then you
dB.
add that to the negative K.
Yes. It will be
That's
negative.
below, yeah?
Yes.
Below 0, which means your gain margin is positive, right?
Okay. Oh.
0
Oh, yeah,
minus
15
the
dB.
gain.
Yeah, 15 dB.
Yeah, right.
Should be roughly. Okay, thank you very much.
Alright, so we're gonna start. Today we will look at some questions in 2018 exam. But before we jump into that, I noticed that I confused a lot of people yesterday because I was rushing through this. So I'm gonna explain the B and C part again. Alright? So for B here, oh well, this question is just having a system like this, and then this is the body plot of your sensor and the wheelchair. These are the questions, right? So in B, it asks that if we want a phase margin which is at least 30 degrees, what is a gain margin in this case, right? So when you are looking for a phase margin which is at least 30 degrees, well, you know that the gain will not change your phase plot, right? So you look for, well, the point, the frequency at which when you add these two phase together, and that gives you negative 150, right? So negative 150 degrees is roughly here, right? This line. Can you see it? Around here, right? And you can find, well, you can estimate that at this frequency, you have this plus this, this plus this, which gives you roughly negative 150, right? And now you go up to the magnitude plot, you can find these two magnitudes, right? So you know that in order to have your phase margin like larger than 30 degrees, you need to have your crossover like at least smaller or equal to this line, right? So which means at least your gain at this frequency should be 0 dB, right? So now you have this magnitude and you have this magnitude, you know that, well, this part is negative, this part is positive. So you add them together, you leave this much positive, right? So you know that you need this much negative to bring your gain to 0, right? So your K roughly sits over here, right? So this much negative that can cancel this part off, right? And also, the lower your gain is, the further to the left your crossover locates, right? So now you have the upper bound of your K, right? And if you have a K at this value, you can then look for your gain margin, right? So you know that this is the frequency that you have your phase add together and become negative 180, right? And you read it up, you find one gain here, one gain here, and another gain here, right? And then you add them up, that gives you roughly, so your gain margin is roughly negative 10 dB. So you just add these 3 up, right? So that's for B. So for C, it is asking whether that it's possible to have a gain that you can achieve steady state error which is smaller than 0.01 and also phase margin at least 30 degrees. So this one is the same as this one, right? Phase margin at least 30 degrees. So from B, you have a upper bound of your K, and as we've calculated yesterday, well, you can just read out the magnitude here, right? Add them together, that is your G0, right? The magnitude of G0, right? So you can do the calculation, and then you found that in order to satisfy your steady state error requirement, you need a gain which is greater than 4.42, right? And apparently, well, this gain is below 0, so it's a small number, right? So which means to satisfy this, you need a large K, but in order to satisfy this, you need a really small K, which means it's impossible to find a K that satisfies both requirements, right? So that was the question we kind of finished yesterday, but didn't really. Okay. All right. So today we're gonna look at the 2018 exam paper. It's in a similar format except that you have 5 questions instead of 4. It's 3 hours, 15 minutes reading time. Everything is in a similar format. Okay. I will start from question 1. Okay, in question 1, this is your system. You have 2 tags, and you have some tube connecting them together. There's an inflow, this is the outflow. So in the question, it is given that you have this relationship between your U, which is your input signal, and Q1 inflow. And then you have these relationships in the 2 tags. Furthermore, you have this, which is about the flow. Right? So question A is asking you to find all equilibria for the system when you're assuming that H1 is greater or equal to H2, which is greater or equal to 0. This gives you the relationship of this one and this one. Right? So basically, these are the equations you need to look at. Right? So find equilibrium. So firstly, when you have well, this is Q1. When you have H1 greater or equal to H2 greater or equal to 0, you have firstly Q1 dot plus Q1 equals to arctan U, where U is positive. You have A1 H1 dot equals to Q1 minus Q3. You have A2 H2 dot equals to Q3 minus Q2. And you have Q3 equals to K3 square root of H1 minus H2. And lastly, you have Q2 equals to K2 square root of H2. Right? These are the equations you have. Right? So what is the first step in finding equilibrium? What is the condition when you are at equilibrium? Yes, so all the derivatives should be set to 0, right? So when you are at equilibrium, you have Q1 dot equals to 0, you have H1 dot equals to 0, you have H2 dot equals to 0, right? And now you're subbing those. You know that Q1 dot equals to 0, so you have Q1 at equilibrium equals to arctan U at equilibrium, right? And for the second one, you have this equals to 0, so you have Q1 at equilibrium equals to Q3 at equilibrium, right? For the third one, similarly, you have Q3 equals to Q2. And third, that's just the same, so you just write it down. Right? From this two, you know that Q1Q equals to Q2Q equals to Q3Q, right? And hence, you have the relationship at equilibrium that you have arctan UQ equals to K2 square root of H2Q equals to K3 square root of H1Q minus H2Q, right? Where U is greater or equal to 0, right? So this relationship captures all your equilibria. Right? Is everyone clear on this? Cool. Okay. So Question B. Linearize the system around an equilibrium for which you have this. Alright. So here are our system equations. Here is the relationship of our equilibrium, right? So B. So when we have the equilibrium point at H1 equals to H1 star, H2 equals to H2 star, we will have, well, again, so this condition is similar to this, so all the equations you had just now are useful, right? So firstly, well, I'll just copy that down. So at equilibrium you have arc10. Well, since they're using star, so I will use star as well. Right. This is from question A. Right. So now you know that H1 star equals to 2H2 star, which means you have right? So you can take any of this. You can then write down your U star equals to tangent of, for example, we pick this one, it will be K2 square root of H2 star. Right? And with this, you know that your Q1 at equilibrium equals to arc10 of UQ, or, well, you just have this relationship. So you also have your Q1 star equals to K2 square root of H2 star. Right? So these are all the parameters at this equilibrium. Right? So now we're going to linearize the system. So again, we had this, we have these differential equations. We can sub in Q3 and Q2 into these two equations, and then we will have a set of equations as Q1 dot equals to, plus Q1 equals to arc10 U, right? The first one I'm just copying down. So for the second one, we have A1 H1 dot equals to Q1 minus, it was Q1 minus Q3, which Q3 equals to K3 square root of H1 minus H2. So you just copy that here, right? And similarly, you have right? So A2 H2 dot equals to Q3 minus Q2, right? So these are Q3 and Q2. So your system is captured by these three equations, right? Now, let's label them. So, firstly, you write everything on one side and let it equals to 0, right? So we define L1, which is a function of Q1 dot, Q1 and U equals to Q1 dot plus Q1 minus arctan U equals to 0. Right? You define this. Similarly, you have L2, which is a function of H1 dot Q1, H1, and H2. That equals to A1 H1 dot minus Q1 plus K3 square root of H1 minus H2 equals to 0. Right? Lastly, you have L3, which is a function of H2 dot H1 H2 equals to A2 H2 dot minus, well, I just shift this forward, so it's plus K2 square root of H2 minus K3 square root of H1 minus H2 equals to 0. Right? That's the first step when you're doing linearization, right? And now you can use the Taylor expansion. Then you can write, well, so eventually we want to write it in a incremental form, right? So we can now also define, we can let so that delta Q1 equals to Q1 minus Q1 star, which is the difference between Q1 and its equilibrium, right? That gives you the incremental model, right? Similarly, we can have delta U equals to U minus U star, right? We can have delta H1 equals to H1 minus H1 star. Delta H2 equals to H2 minus H2 star. And from here, you have that delta Q dot equals to, sorry, Q1 dot, because this is a constant, right? When you are taking derivative, this will be 0, right? So your delta Q1 dot will just equals to Q1 dot, right? And similarly, you have delta H1 dot equals to H1 dot. Delta H2 dot equals to H2 dot, right? So this is just for preparation when you are writing it, well, when you are organizing it into a incremental form, right? So now let's do linearization. So for the first one, it is equal to L1 when you evaluate it at Q1 start dot Q1 star U star, right? This is at equilibrium, you sub them in, plus partial derivative with respect to Q1 dot when you evaluate at the equilibrium point, right? And this will be multiplied by Q1 dot minus Q1 start dot, which is 0, right? And you do the same thing for each of the parameters. So by definition, this term equals to 0, right? Because you are at your equilibrium point, right? And now we need to calculate all those partial derivatives. So for Q1 dot, it's just 1 times this, which is delta Q1 dot, right? And then you have Q1, which is just this term, again 1 times, and this is just delta Q1, right? Then comes to U, it's a negative term, so minus. So the derivative of arctan is just 1 on 1 plus U squared, right? So you have 1 on 1 plus U squared, and you just sub in U equals to U star, and then times delta U, right? So this gives you delta Q1 dot plus delta Q plus delta Q1 minus. So from the beginning, we have your U star equals to tangent of K2 square root of H2 star, right? So here we put that in 1 on 1 plus tangent squared K2 H2 star, right? Right? And that equals to 0. Because that's the same equation. Right? Well, it's an estimate. Right? So this is the first equation after linearization. Right? So you do similar things to the second one and third one. So for the second one, H1 dot Q1, H1, H2, it will be, you put in all the equilibrium points. Subbing those. Right? Right? So again, this term equals to 0, and here you have A1 times delta H1 dot. You have -1 times delta Q1. This is for H1, so you have, that's K3 on 2 times H1 minus H2. And you need to sub in H1 equals to H1 star, H2 equals to H2 star, and that is delta H1. Right? And lastly, for H2, well, it's a negative sign. right? That gives you A1 delta H1 dot minus delta Q1 plus, so you know that from the question you have H1 star equals to 2H2 star, right? So here, this will just be H2 star, right? So 2H2 star delta H1 minus A3 over 2H2 star delta H2, right? That's for the second differential equation. And for the third one, you have right? Again, this is 0. You take partial derivatives. So it's here, right? So you have H2 dot, you have A2 times delta H2 dot. And for H1, you have negative K3 over 2 times H1 minus H2, and you sub in this. For H2, you have 2 terms. The first one gives you the second one gives you, well, it's actually you have negative sign here, so it's negative K3, right? And you sub in H1 at equilibrium, H2 at equilibrium, delta H2. Right, that gives you A2 delta H2 dot minus, again this is just H2 star, right? K3 over 2 H2 star delta H1. This is again square root of H2 star. This is also H2 star, so you can merge them together. So you have K2 plus K3 over 2 times H2 star and delta H2. Right? So 1, 2, 3. That's your linearized model, right? Alright, so we've done linearization now. For C, it is asking that assume you're measuring this, and you have a controller of this form. It's saying, the capital delta US is the Laplace transform of delta U. RS is the Laplace transform of your reference. Capital delta H2S is the Laplace transform of your delta H2. Right? C1 and C2 are appropriate transfer functions, and it asks you to draw the block diagram of the linearized closed loop system and label the signals and transfer functions. Right? So, from B, from the linearization, you got delta Q1 dot plus delta Q1. I'm just copying those three equations down. Minus 1 plus 10 squared K2 H2 star equals 0. We have A1 delta H1 dot minus delta Q1 plus K3. Right, these are the linear equations you have, right? I'll just make it consistent, so I will take, so that everything is on the S domain, so I'll just take Laplace transform, and that gives you, we define capital Q1 is the Laplace transform of delta Q1, right? And we define delta H1S is the Laplace transform of delta H1. Right? And then together with this, you have all of them covered. Right? So if you take Laplace transform, you have S delta Q1S plus delta Q1S. Well, I'll organize all the derivative terms on one side, so I'll write it in this form. That's the first one. Second one. Right? So you can further write this, you can see that the coefficients here are the same, so you can write it in the form of it negative. And here you can organize this together, right? So you have and minus right. And as provided by the question, you also have delta US equals to C1S RS minus C2S delta H2S. Right? So now we can draw the block diagram based on these 4 equations. Right? So firstly, you start with this. So you have your delta US somewhere, which has 2 terms added together. So the first one is RS. RS times C1 S, of course. That's added here, and then you can see that you need to subtract C2 times somewhere you have H2S, right? And now we look at where your delta U comes in and affects, right? So you can find your delta US here, which affects your delta Q1, right? So you know that you need delta Q1 and S times delta Q1, right? So you need at some point, you have a integrator which converts S times delta Q1S to delta Q1S, right? And you know that your S times delta Q1S is this times delta US. So here you have 1 over 1 plus 10 squared K2 square root of H2 star. Yep, sorry, you need to have a note here. And you need to subtract delta Q1S, which is just here, right? So with this, you have your S times delta Q1S equals to this times delta US minus delta Q1S, which is this equation, right? And now you can see that your, sorry? Here? So here is converting S times delta Q1S to delta Q1S, right? Sorry, I can't hear you. So well, if you write well, so this is S times delta Q1S, right? So this also equals to the summation of this one and this one, right? Well, actually you subtract this, right? So this minus this, right? That's a summation node, right? So this signal is this transfer function times delta US, and here it is connected to delta Q1S, right? So from here, you get exactly this equation, right? So this signal equals to this minus this, right? Okay, so now you can see that the second equation has Q1s, delta Q1s involved, so it's here, and this one relates delta H1s and s times delta H1s, right? So again, you know that you have a integrator. On the left hand side, you have s times delta H1s. On the right hand side, you have delta H1s, right? So, what makes s times delta H1s? So firstly, you pre-multiply by 1 over A1, which gives you, so here, it's actually A1 times S delta H1s, right? Which equals to, again, a summation here. You have your delta Q1s coming in, right? And you need to subtract something times the difference between this and that. And this is here, that is here. Here. Right? So you can so here gives you the difference between this and this. Then you multiply by this, and that need to be subtracted from here, right? So from here it gives you, so this one is A1s delta H1s, right? So here it gives you A1 times S delta H1s equals to delta Q1s minus this times the difference between these two, right? Sorry, this times the difference between these two, right? Okay, and now you have this part missing, which corresponds to the third equation, right? So from the third one, of course, you again has a integrator, and behind this integrator you have s times delta H2s, right? And in order to get this, you need to multiply by this. And now here, this signal is A2 times S H2S, right? And that equals to, again, summation. You have this term, which is exactly the same as this term, right? So this term is the same as this term. And we already have that here, right? Right? So we can just drag it here. That's a positive term, and then you need to minus. So your H2 delta H2s is here. You need to minus. Well, this is the same line. You can drag it back. Should be minus. So here it's like you have your A2 S delta H2S equals to this term, which is this line. Sorry, this line, this minus this, right? So this line is this times the difference between delta H1S and delta H2S, right? Minus this times delta H2S, right? So that gives you the third one, right? So this is actually the block diagram of your system. So if you prefer another way to do this, what you can do is that you have all these equations, you take Laplace transform, you organize the terms, eventually you can derive a transfer function for your plant, if you like. And then you can also draw it in a cleaner way, but in that case you need to calculate the transfer function of your plant and clearly note it down, right? So this is directly derived from the equations. You can also do Laplace transform and have a simpler block diagram, right? So this is for this lecture. So in the afternoon we'll go through more past exam questions. Right? See you in the afternoon. I'll still be doing 2018 questions. I'll probably cover question 3 and 4.
Which one?
So 3 will be... Okay. That's a root locus question.
Yeah.
And question 4 is a Nyquist problem.
Okay. Can I ask about one of the other ones? Or we do not?
Which one?
One of the other 2018 questions.
Which one?
That's the one with like M and K or something. Yeah.
This one? Sure. But I think we need to get that.
Yeah.
The question said we need to find the sign chain of the first column, right?
Yes.
So does it mean we need to compare the first column sign with the original polynomial?
No, so well, no matter if the first one is positive or negative, you just look at the number of sign changes, right? So if the first one is negative, all of them are negative, then you don't have any sign change, which means it's stable.
The first one you mean
So, well, I mean, for example, this is negative 1, then all of them are negative. You don't have any sign change. So that means your system is stable. But if your first term is positive and the following ones are negative, then you have one sign change, which means you have one unstable form. So just focus on number of sign changes.